Hi, this video is going to talk about moments and moments generating functions. Moments and moment generating functions are introduced in the textbook in section 3 of chapter 2. So this is the part of that section that we kind of skipped the first time through. You want to go back and read it now. So first of all, when we talk about the moments of x, we've talked about the mean, mu, or the expected value of x. And another name for this is calling it the first moment of the random variable x. And in general, the nth moment of x is the expected value of x to the nth power. Okay, so that's what we mean by the moments of x. Now, the moment generating function for a random variable x is defined for all real values of t and I'm going to try to make my t's like this so we can tell the difference between a t and a plus sign. And the way that we define it is the moment generating function is the m of t is the notation we use for them, and it's equal to the expected value of e to the t times the random variable x. And if you remember the way that we find the expected value of a function of x, if we're working with a discrete random variable, what we'd be doing is we would be summing over all of the possible values of x, this function of x, e to the tx, times the probability that x equals that value, little f of x. So that would be for the discrete case. If we're working with a continuous random variable, we would integrate over all possible values e to the tx times f of x dx, and that again would be for continuous random variables. So there's these are the ways that would define the moment generating function m of t. Now the reason that the moment generating functions are called the moment generating functions is because we can find the successive moments of x by taking derivatives of the moment generating function. So for instance, if I want to find, if I take my moment generating function m of t, and so that is the expected value of e to the tx, then the first derivative of the moment generating function is the derivative of the expected value of e to the tx, which in fact is equal to the expected value of the derivative of e to the tx and that gives me the expected value of x times e to the tx. And so if I evaluate this at t equals 0, we get the expected value of x times t to the 0, e times t to the 0, which would be 0, so it just gives us the expected value of x, or the mean. Right, so by taking the first derivative and evaluating it at t equals 0, I get the first moment of x. If I want to get the second moment of x, I can use sort of similar math to show that the expected value of the second derivative of the moment generating function comes out to be the expected value of x squared times e to the tx. So if I evaluate the second derivative at t equals 0, I get the expected value of x squared which is my second moment of x. So I could continue this to find the third and fourth moments and things like that. Now, what's especially useful about this is that I can use it to find the mean and the variance. The mean I already saw that I can find by taking the first derivative of the moment generating function and evaluating it at 0. Because the variance of x is equal to the expected value of x squared minus the mean of x squared, the expected value of x squared is the second derivative of that moment generating function evaluated at 0, and I can subtract off the mean, which is the first derivative of the moment generating function evaluated at 0, and then squared. Right? So I can use the moment generating function to find the mean and the variance. So some important characteristics of moment generating functions. First of all, it's important to remember that the moment generating function, m of t, is a function of t, not of x. So when we're taking derivatives, we take them with respect to t, not with respect to x. The second thing we already saw, that if I want to find the mean, which is the expected value of x, or the first moment of x, I can take the first derivative of the moment generating function evaluated at 0. We also saw that the variance of x, sigma squared, can be found by taking the second moment, so the second derivative of the generating function evaluated at 0, minus the first moment squared. As I say, we already mentioned that. And then the other thing that's very important is that the moment generating function actually uniquely determines the distribution. So for instance, if two random variables have the same moment generating function, that means that they have to have exactly the same distribution. The other thing I'll just mention quickly is that there are some random variables that do not have moment generating functions, but most of the ones that we're going to work with here do. Okay, so I'm going to do an example. We're deriving the moment generating function of a binomial distribution and looking at how we can use that to find the mean and the variance of the binomial distribution. So I'm going to work with a binomial. X is a random variable that's a binomial with n and p. So my moment generating function, m of t, remember, is the expected value of e to the t times x. And in this case, that means I'm going to be summing from k equals 0 to n, because those are all the possible values of a binomial random variable with n trials. E to the tx times the probability that x equals k, which would be n choose k times p to the k power times 1 minus p to the n minus k power. Doing a little bit of math. Sorry, this should be k. Right? There we go. E to the t k. K is taking the place of my t. Just want to be consistent so that when I simplify, things make sense. Okay, so now I have p e to the t to the kth power times n choose k times 1 minus p to the n minus k power. And we can use the binomial theorem to find that this is equal to p times e to the t power plus 1 minus p to the nth power. So there's our moment generating function for a binomial distribution. Now, if I want to use this to derive the mean and the variance, I'm going to start by taking the first derivative of this moment generating function. So it's going to give me n times p to the e t plus 1 minus p to the n minus 1 times p e to the t. And when I evaluate this at 0, I get n times p plus 1 minus p to the n minus 1 times p times e to the 0, which gives me n times p. And if you remember, for a binomial distribution, this is my mean, n times p. Now if I want to find the variance, I'm going to start by finding the second derivative of the moment generating function. This is going to be n times n minus 1 times p e to the t plus 1 minus p to the n minus 2. I'm going to have to go on down onto the next line here. Let's see, maybe I don't. Let me scooch myself over a little so I don't have to do something weird there. Okay. Let's see, p e to the t plus 1 minus p to the n minus 2. Then I multiply that by p e to the t squared plus, scooch over some more, n times p e to the t plus 1 minus p to the n minus 1 times p e to the t. Okay, so that's a little bit of a large production here. But if I evaluate this second derivative at 0, I get n times n minus 1 times p squared plus n times p. Now, if I want to come back and find my variance, my variance is going to be this second derivative of the moment generating function evaluated at 0 that I just found, minus my mean squared. So this gives me n times n minus 1 times p squared plus n times p minus n times p squared, which is going to simplify to give me n times p times n minus p squared, which if I factor out the n and the p is n times p times 1 minus p. And if you remember, that is our old formula for the variance of a binomial distribution. So one of the ways that moment generating functions can be useful is that they often will give us an easy way of finding the moments. I'll derive a moment generating function for a continuous random variable just so that we can see how that would work. I'm going to do an exponential random variable so that x has an exponential distribution with mean theta. In this case, the expected value of e to the tx. is going to be found by integrating over all the possible values of x. Exponentials only take positive values, so that's going to be from 0 to infinity, of e to the tx times my probability density function, 1 over theta, e to the minus x over theta dx, which gives me 1 over theta times the integral from 0 to infinity of e to the minus 1 over theta minus t times x dx, which is going to give me 1 over theta divided by 1 over theta minus 1. Sorry, 1 minus 1 over theta, let me just look at this. There's 1 over theta minus t, not minus 1. Which if I go through and multiply top and bottom by theta, I can simplify to 1 over 1 plus theta times t. And that would be my moment generating function for an exponential distribution. So as I mentioned, one of the ways that moment generating functions are useful is that we can use them like we did with the binomial to find the mean and the variance. But the other thing that's useful about them stems from the fact that, as I said, moment generating functions uniquely determine a distribution. So for example, if I know that a binomial distribution has a moment generating function of the form p e to the t plus 1 minus p raised to the nth power, so if x has that moment generating function, then I know that x must be binomial with parameters n and p. So if the moment generating function, for instance, were m of t is equal to 0.2 times e to the t plus 0.8 raised to the 50th power, well, in this situation, p would be placed taking 0.2 would be taking the place of p, 1 minus p would be 0.8, and n would be 50. So if x has this moment generating function, then x must be binomial with n equals 50 and p equals 0.2. So I derived the moment generating functions for a couple of our common distributions that we work with. These moment generating functions can all be derived, and I didn't derive them all individually here, but if you'd like to look through, the derivations are all pretty much in the textbook. And it's going to be useful later on as we're working on finding distributions of functions of random variables, and especially of sums of random variables, to sort of have a little bit of familiarity with forms of these moment generating functions. So I'm going to post this sheet online as something that you can work with, so that you can look at recognizing the forms of moment generating functions for different types of sort of common distributions. Okay, so just to summarize, moment generating functions are functions of t. They're the expected value of e to the tx, where x is the random variable in which we're interested in. One of the ways that they're useful is for deriving the moments. Of the random variable x. The other way that we're going to see as we go forward in this unit is we're going to see that they're also extremely helpful for deriving distributions of sums of random variables. And really, it's this piece that we're going to take big advantage of in this module. So as you go forward, hopefully seeing the moment generating functions at this point in time is helpful, because you'll see more than you would have if we had done them earlier in the semester, that they're really important and powerful tools for deriving distributions of functions of random variables. Okay, I'll stop there. Thanks for watching.